Okay, I think we'll get started. I'll follow Ben's thing and not use the microphone if that's okay. My name's Aaron. This is thankfully my third trip to Tokyo to talk at the conference over the years. Very happy to be back. If I sound a little croaky, I'm just a bit unwell after the travel, so hopefully we'll be all okay. A little bit about myself before we get started. I have been using Cassandra since version 0.4. I co-founded with Nate a small company called The Last Pickle. We have 15 staff around the world in 5 countries, and we help people use Apache, Cassandra, and a couple of the other things in the ecosystem. I'm a committer and a member on the PMC, the Project Management Committee. And what I'm going to talk today about is kind of zooming out from what Ben started there with all those great kind of tips on how Cassandra works into how we solve problems for people at TLP. Some of the problems we've solved are diagnosing split brain gossip things in 300 node clusters, dealing with performance, rolling out changes into thousands of nodes and things like that. So let's start by the types of problems. And then we're going to look at how we process and how the different parts of Cassandra can help us solve them. So I think that we generally are doing 2 things. We're either optimizing things or we're troubleshooting problems. So we've got 3 roughly things we're going to want to optimize out there. To start with throughput, which is just how many things we can do in a certain period of time. In general, it's about 7,000 to 12,000 local requests per core per second. It's kind of ballparky for what you want to get there, because the first thing it might be that somebody just wants to put too much traffic through a machine. So we're going to get out there and optimize this throughput. Next, we're going to optimize latency, and this is just how long it takes. But we can break this down. How long does it take from the perspective of the client? How long does it take from the perspective of the coordinator of the request, so at the cluster level? And how long does it take from the perspective of the local node that's reading and writing things? How long does it take for things to get in and out of memory? How long does it take for things to get on and off disk? We can break latency down into lots and lots of different areas. Now, typically, we would expect that a write would take on the order of sort of 30 microseconds up to maybe 80 microseconds to happen on the node. And then at the request level, so from the Cassandra perspective, without really knowing too much about the data model, about a millisecond or so. And the read might take around 50 microseconds up to about 300 microseconds, depending on what's happening, how much data you want to get. And again, without knowing too much about the data model, from a cluster-wide, from a request perspective, that could be up to kind of 3 to 5 milliseconds, depending on how much data you want to get out of there. And lastly, kind of the most important thing, which is optimizing cost. So how do we increase the density? How do we serve the same traffic with less hardware? How do we use cheaper hardware? If you're on a cloud platform, maybe you're moving from ephemeral disks onto EBS, or you're moving from one cloud vendor to another because they've given you a deal or something like that. And I think once we make something, operations is just about reducing the cost to serve. Keeping it running, of course, but basically you're just trying to reduce costs the whole time. The other type of things we deal with are troubleshooting. And there's only 2 spots here, I think. We're troubleshooting availability, so can we actually run a request? The strange thing about a system like Cassandra is that some requests will be able to run and some won't. So you can get these temporal failures or partial failures. As Ben was describing, the token model means that it may be down for some data but not for others. And the other issue that we often troubleshoot is consistency. As Ben was showing, there are timestamps used to work out which value to show. He was talking about it at the local level. So when a node takes some data off disk and tries to work out what value, we also do that at the request level. The coordinator is doing that with the data that gets from different replicas and working out. We know about the consistency level and the timestamps, and sometimes we just get inconsistent data back when we feel that we should. So, how do we solve problems? We've been doing this for 6 or 7 years. We started off just bashing keyboards, and after a while we started to think about it and delve into it a bit further. So there's a couple of anti-patterns, things that you shouldn't do. The streetlight method, and these are from a book by a guy called Brendan Gregg, and we'll talk about him a little bit later on as we go. The streetlight method is basically, you've got a tool and you can shine it on something, and you shine it on the thing and you try to guess that, well, the bit I understand here works this way, so I'm going to just guess that the bits I can't see are doing what I think they're doing. I'm not going to understand, I'm just going to understand this one bit. Another way to talk about this is the saying, if you've got a hammer, everything looks like a nail. So if you know 1 or 2 tools, you just shine those 1 or 2 tools onto the platform. Next thing is just randomly change stuff, which can be kind of fun. Don't forget to change it back though. Sometimes you do have to just take a guess and hope, but it's not a great process, and it's normally the last thing to do. And then the easy one is just blame someone else. The way we do this is if somebody's got a multi-data center cluster that's running over a wide area network link, so maybe it's transiting over the internet, we go blame the internet and we say, your cluster's not working because you've got traffic running over the internet and it's getting lost or something like that. It's the easy one. But what we do when we're working through problems is we use a technique called the OODA loop, which stands for Observe, Orientate, Decide, and Act. And this was this became known to me back in 2011. There was a company called Boundary, and one of the co-founders there, called Ben Black, did a talk at an O'Reilly conference and talked about this process. This was created by the US Air Force when they created their first Top Gun school, and it's a way of making decisions and trying to understand the world around you. You start by observing things. You can see here unfolding circumstances, outside information coming in. You then orientate to try to work out what you think is the world is happening, and there's a bunch of biases that come in on that, your cultural traditions and things like that. You then make a decision, and maybe your decision is I don't know, so I have to go back and look at some more stuff. But then you may take some action, and if the world hasn't fixed itself, you have to go back and do the whole thing again. And this is a process that we use, and I'm going to spend the rest of this talk walking through how we use the tools that Cassandra has, and how we use our understanding of how Cassandra works to be able to do this to solve problems. We also find that we actually write down in our tickets a heading. So if we're solving a problem for a customer and it's a complex thing, we're doing a good job with it, there will be a heading that says observations. And it's just, I can see this, I can see this, I can see this. There'll be a heading that says orientate. And it's like, this is what I think is going on. And then there's a heading that says decide. This is what I think I'm going to do. And then there's a thing that says action. Here is me doing it. And that's a great way for teams to work together because I can pick up that ticket and understand pretty quickly why somebody else did and why. So let's start with our observations. As I said, what can I see? So this is an undirected exploration, and that's pretty hard. So you don't want to bias this. See, normally you start with a guess, or you start with the problem. And then as we iterate through, you're going to bisect down and get closer and closer to what the issue is. Now, before we do that, we need to talk about time. Whenever you are troubleshooting with Apache Cassandra, time is something you are going to have to encounter and get used to and understand that it's kind of bonkers. Here's some scale for time. So 1 second, the second is the second row down there, and here is how they scale across. Okay, so we mostly care about milliseconds and microseconds when we're fixing problems with Cassandra. As I said earlier, if it takes 20 microseconds to write your request, there's a bit going on there, and we're trying to understand what's happening in such a small amount of time. So here, microsecond is a millionth of a second instead of the thousandths of a second for a millisecond. You get 1,000 microseconds per millisecond. Okay, how does that translate into the real world? Again, this kind of shows a scaling here. So we've got one CPU cycle, which is 0.3 ns, which I think is, I always get this confused, nanoseconds, very small amount. CPU fetch cycle, get a command, go do a thing, store it. We've got our cache access here, and you can see on the right-hand column, they're scaling up as to how long it takes. So if it takes 1 second to do a fetch cycle on the CPU, it takes relatively 6 minutes to go to main memory and do something. Now, these numbers are kind of old. I've seen them around for at least 3 or 4 years. Computers have gotten a bit faster, but there's physics involved here, and whether the numbers are exactly right now or not, the general idea is hitting caches, nice, going to memory, slower, going to solid-state disks, slower, going to relational disks takes forever, touching the network takes a long time. I don't trust these ping times from SF to Australia or SF to the United Kingdom. I did a talk in London a couple of months ago, and I had the latency numbers on there, and it was more like 180 milliseconds, I think. So, time, lots of small windows of time, and we're trying to work out what Cassandra is doing in these small windows. And for us, we think that time flows in one direction, which is our general experience of things, which is fine because maybe we made up time, maybe it exists. I'm not that good at physics. But for computers, time does not flow in one direction in a sensible, consistent way. It can stop, and it can, as in leap seconds, when they get inserted, and it can go and jump forwards and backwards, and every machine can have a different time. And we've dealt with this problem at a human level a long time ago. Back in the Industrial Revolution, in England, in the United Kingdom, the time was the guy made the factory, he had a bell, he rang the bell, that was the time to go to work, he rang the bell, that was the time to end work, that was the time. Then they started having trains, and the trains you had to have a schedule about where they were going to go, and so the Great Western Railway, which was also employed Isambard King de Brunel, who made huge boats and did all sorts of fun things, they created the idea of railway time in the 1800s, and that was when we started to have a coordinated time around the place. So computers in a cluster are kind of like early Industrial Revolution England. Everybody's got their own thing, and everybody tracks according to their own time. And instead of railway time, we have network time protocol, NTP, which generally you don't have to do anything about. You don't even think about it. You can, though, look up NTP drift, and it's part of the stuff that we collect all the time. And occasionally you might have an insane problem which has to do with NTP drift. If you're troubleshooting consistency, because we know consistency has to do with time. Okay, so back to what can I see, and how do we do this in an undirected way to begin with. So logs are very, very important. I've done some guest lecturing at a local university, and I tell the students they just learn to read logs better than anyone else, and you'll make a lot of money, because reading logs is a skill, and joining them up to code. Take very good care of your logs. Aggregating them is a good thing to do. I'm not a big fan of the syslog because it doesn't handle multi-lines. It breaks them up. And so if you get an exception stack coming out of Java, it's across multiple lines. You can observe things using some of the no-tool commands that Ben went through earlier on, cfstats, aka table stats now. This is an example from a 2.2 cluster. It's got lots of stuff in here. We've got in here Bloom filter false positive ratios, which is how many times we did a seek on disk that we didn't need to. We've got down here how many live cells and tombstone cells, things that Ben mentioned. Lots of stuff, really handy, but it's on the command line, and it's great if you're SSH'd into a box and you're trying to understand it. It's a good starting point, gives you a big overview of what's going on per table. CF histograms, column family histograms, dives a little deeper in. This has got some performance metrics in here. What this is telling us is how many micros, there's our time component again kicking in, how many microseconds it took to do writes, reads, in a percentiles. In this example, it was just reads. Tells us how big the partition sizes are, so those partitions that are driven by the partition key. In this case, they were pretty small, and how many cells. A cell is roughly a non-primary key table, in your CQL, non-primary key column in your CQL table. If you want to go a little bit deeper into things, we can look at this thing TP stat, which stands for thread pool stats. Cassandra uses an internal architecture called CEDAR, Staged Event Driven Architecture. There are logically a number of thread pools that your request flows through, and it's hard to make this format nicely, but you can see here we've got a mutation stage, a read stage. You can kind of guess what they do. Mutation is write, read is read. Request response, read repair, all these different places that we're going to. It counts how many times we did a task there. It says how many things are active. And it counts, importantly, how many of them were blocked, meaning that there was something stopping them from going and doing their job. At the bottom of it, it has this output here of how many of them were dropped. Part of the staged event-driven architecture is an idea of load shedding. If a client is no longer waiting for some work that it's asked us to do because it's timed out, and we know that will happen because the coordinator will time out waiting and tell the client that couldn't do the work, I'm not going to do the work because maybe my disk disappeared for a little bit and I've got a big queue of things, I'm just going to drop things. We can go a little further down the path here. We can go down and look at I/O stats. I/O stats gives you the disk level things. This is I/O stats -X, and then you say something like 5, and it prints out every 5 seconds. It says on this device, and there's a bunch of stuff here, and actually the best help I ever found for I/O stats was Jonathan Ellis's old blog back from before DataStats even started. He had a great page on there that explained these things. The bits we actually care about are the wait. We've got a read await, and a write await. That's how long requests are taking, are sitting there waiting for their data to either be put on the disk or taken off the disk. And average queue size, AVG QSD, which is how many things are sitting in a queue, how many requests are sitting in a queue waiting to get some work done. And we can go in further. We can do the similar thing for the network. We can go down to network stats, and this is net stats minus TNAP, I think, off the top of my head. This gives us all the connections and the size of the queue. So remember earlier when I said I'd like to blame the internet when things are going slow, you can run this little guy and you find out that the queue is too big, then you can go and blame someone else. Now, there are a lot of tools out there, and learning the OS tools is a difficult thing. This is a really handy picture from that guy, Brendan Gregg. He's done a lot of work on performance diagnosing, come up with some formal methods, written lots and lots of tools. I believe he's at Netflix now. He has a GitHub page with a bunch of tools on it. So if you want to get deeper into that side of things, it's a great resource to go. So I was kind of complaining that while no tool has a lot of great things on it, it's mostly on the command line, and metrics are better. Now, we think that metrics are a great thing because you can take the metrics from your Cassandra cluster and put them into something like Grafana with Prometheus or Graphite backend or Ganglia or Datadog or whatever, and you can put them in there with metrics from your application stack. And then you can build a nice little chart that has the latency that your application sees, the latency that Cassandra sees, the latency that will way down. And you can do the similar things with request throughputs and that type of thing. Now, the metrics library that Cassandra is coded against is called Metrics. It's part of the Dropwizard project. And it's the same library that is used by Kafka and Spark and Hadoop and basically everything in the Java-based big data platform. There are ports onto multiple different languages, and it would encourage you to have metrics coming from your application that are on the same technique and the same world as the metrics coming from your infrastructure, and put them all into one place so you can match them all up. Now, Cassandra has a lot of metrics. There is a wiki page that explains it. It's a pretty well updated page, and this didn't used to be around. I'm going to go through just a few here to give you a flavor of the types of metrics that are around. There are lots and lots. So we're diagnosing throughput. So there's a cluster level throughput. Now, this says OACM, which stands for Org Apache Cassandra Metrics. If you're looking at them through JMX, you'll see that. If you're looking at them through the way that you can push the metrics out from metrics library to something like Prometheus. Sorry, Prometheus is a pull to Graphite. They will look roughly like this as well. So this says, acting as a coordinator, how many requests for write and read did I do in 1 minute? But it's a little more complicated than that and slightly more confusing. That says latency, but it has the throughput on it. It's just the way it's implemented. The 1 minute rate says, how many things did I do per second, and then exponentially weighted average over the last 60 seconds. So this is giving us per second throughput, but not the per second throughput, and exponentially weighted average of per second throughput. Now, that's at the request level. We'll talk to the coordinator. The coordinator has a job to do, and one of those is to send data to the replicas. So when we get down to the node level, we also have metrics, and generally these things are 2 or 3 times bigger than the metrics at the coordinator level, because we normally use a replication factor of 3. Writes go to all the available replicas, and you're either going to be reading, 90% of the time you're probably reading at 2, depending on the read repair chance and your consistency level. So there are these for every table that you have out there. So collecting metrics can get expensive on the storage side. If you have lots of nodes times lots of tables, there's lots of metrics. Now, we can look at latency at the request level. So there is P95, the 95th percentile, the 98th, the 99th, the 85th, the 75th, the median, all sorts of things. And this is going to give you the percentile in microseconds. So you're going to scale that when you go to look at it, and go back to the chart at the beginning. And we've got the local table latency as well. So how long did it take me to read and write bytes off disk, as we were talking about earlier on. These can be pretty small. These can be sort of 30 microseconds, something like that. Again, some for every table. Then we get into the more complicated parts, which is reading off disk. Generally, writes are pretty simple. There's not a lot of moving parts. There's not too many concerns with writes. Reads are more complicated. And some of these metrics here touch on the things that Ben was just talking about. We've got the live scan histogram, which is how many cells did I pull off disk in a histogram. So P95 there would tell me 95% of the read requests that we processed over the sliding window that this runs, we read 100 columns, or we read 100,000. And Tombstone scanned histogram matches with the other one that Ben was saying, that ratio between dead data and live data. And we've got the SS tables per read histogram, which is how many random disk seeks did we do to get that data out. So, yay, there's lots of metrics. Boo, there's lots of metrics. It can get a bit confusing to try to work out what it is. We think that you should be doing this in a dedicated metrics tool. There's no data stacks here. Op Center is great, but you should also have this in a dedicated metrics tool. So we've worked with Datadog, which is a company we love because it's really easy for, if our customers have Datadog, for us to be able to see their data without having to go through all sorts of dances and things. And we love Grafana as a internally hosted way, no matter what the back end is. And we've made some dashboards, and you'll be able to get hold of these soon, or they're out. This is an overview dashboard. So if you're using Datadog now, you will get the TLP dashboards. This is our combined kind of way we want to look at things over all our stuff. There's an overview dashboard, and there's just lots on here, and I don't have time to go through it. Somebody did a talk on this in Austin last week, and all they did was talk about what is on these, which is why my slides look a little bit different in color, because I stole them from him. Okay, so we've just got the overview here of what's going on. We've got the write path, a bunch of stuff in there, write path there. What nodes are doing what. We've got the read path, those metrics I was just talking about, and here, the reason we wanted to do this was because there are so many things there. We wanted to kind of put the things together that we thought were important. So GC pauses, those live scan histograms, tombstones that we were talking about, and all those types of things, and pick the percentiles that we care about. This one is just looking at the SS tables on disk. Again, it's all the read path, and SS tables on disk, sorry, probably touches all of the terrible things that go wrong in Cassandra. Like the read path is the thing that most people are complaining about, and that's sensitive to compaction and repair, all of which is just about monkeying around with those SS tables on disk. And as we were talking earlier on, they're immutable, and so we're working on that. So to work with them is hard. Have a look on the Datadog website and the TLP website over the next week. I think we'll start to do some publicity, just put up a blog post to explain where people can get them. I think our Grafana ones are coming out a little bit in a couple of weeks, Datadog in a week or so. I only run the company, so I don't know what actually happens in it anymore. And you'll be able to get these, and the Grafana ones, I believe, will be just sitting on GitHub or something like that. So we're going to run around and take a bunch of readings and try not to poison our thinking. So then we're going to get to this stage where we're like, okay, so I just saw all this stuff, and what is happening? And we're going to try to do this without thinking about what the solution is going to be. I think that is the biggest mistake that people make diagnosing problems in production, is they start with what they think the solution is and then try to match that, then try to make the problem fit. We talk about in TLP a thing called beginner's mind, because I read this book a few years ago and it really stuck with me. And the quote is, like, in the expert's mind, I always get it wrong. In the beginner's mind, there are many possibilities, and in the expert's mind, there are a few. So we try to have a beginner's mind and try to forget problems that we solved yesterday, because that will often makes it harder to solve the problems we want to do today. Before we try to do this orientate step, let's just take one step back and try to work out what it is Cassandra actually does. Because we're going to need to break it down and try to work out what those bits that are doing. So we take bytes off the client machine, put them on the network, they go over to the coordinator. The coordinator makes copies of them and sends them out to the replicas. And in a little bit, Jason's going to explain how that happens, or how it happens now. We get over to the replica and we take those bytes out of memory and we put them on disk. It's really pretty simple. This is all the database does. We have a little bit of this extra step in here where we have to make it work out what it is we want to return back on reads. But we're just taking some bytes from memory, putting them on disk, taking bytes from disk, putting them in memory, a bit of network transmission in there. We reverse it around when we're doing reads. So this is a stack diagram I made back in 2013. And I did a talk called Cassandra Internals at the summit in San Francisco. It's still pretty relevant. And the talk that I did is on YouTube, and it's still pretty relevant. And it gives just an overview of the different tiers in Cassandra and the different packages in there and what they're doing. And this is the steps that we go through. Clients talk to the API, they talk CQL. There's a tier I call the Dynamo tier, which is working out, well, who's got this data and where should I go and that type of thing. Who's up and who's down. Those Dynamo tiers talk to each other between the different nodes. Then they talk down to a database tier, which is a log structured merge tree, but in 4. Cassandra 4 will be a pluggable storage engine, as Nate was talking about this morning, with RocksDB in there. And then that goes to disk. So it's pretty simple stuff. But if we're armed with just this little bit of knowledge, then we can start to understand what are the different systems that are out there. We're going to have to think about what each one's trying to do. So, what are the clients seeing? Are they seeing exceptions or not? Great way to do that, logs in the application, metrics in the application. At the cluster level, what's our throughput and latency? Are we throwing any errors that might be considered from that dynamo here? And a good way to do that is understand what view of the other nodes each node has. So there are more node tools for that and metrics. There's one called node tool, gossip info, which dumps the internal gossip state, which is how the nodes are talking about each other. There's one called node tool net stats, which dumps out information about how the nodes are talking to each other at the binary protocol level, which nodes are timing out, that type of thing. You've got those drop messages that we saw before. We've got how's the storage engine performing? How are we getting stuff on and off disk? The throughput and tombstones and the SS tables per read and all the things we've seen. This is the database tier. How is that performing? What's the OS doing? And we looked at a couple of tools for that, IO stats, net stats, had that big diagram. Can we understand what state the disk system is in, the network system? So it's the network behavior. What decisions is the coordinator taking to work out what result to give back to the client? Again, there are some things we see about that. There is a thing called read repair, and it gets called read repair active and passive, I believe, nowadays. One of those is, oh, we got some data back from multiple nodes, and there was a mismatch, so we had to go and run the request again to work out what data to give out, things like that. As always, is the JVM behaving well or not? Normally not. I mentioned compaction is the thing everybody complains about. We can see if the compaction's keeping up. We can look at the node tool compaction stats. Is repair running? Is hindered handoff or read repair running? We get asked lots and lots of questions, but the general way that I try to do this is work from the client into the disk. And in that kind of model of what we're doing here and what those different systems are, try to understand what each one's doing just from the evidence that you've got. So I'm going to build a model of what each system is doing based on the evidence. I only try really hard not to guess, and then decide what to do. So at this point here, I'm going to say, well, because Y is happening, sorry, I think we should do something. Now, before we do that, let's just go a little bit deeper into how Cassandra does what it's going to do, all those different tiers. The only thing it's going to do is follow the code. Right? There is nothing else it can do. And it's kind of complicated code in some places, but it's also kind of basic. There are some inputs to it, which is the configuration and the requests and the data that flows in. And there are some outputs, which are the results and the metrics and the logs and all of the tooling that's there. And all of this allows you to predict what will happen now, to understand what will happen, what's happening now, and to predict how things will change when you change configs and that type of thing. The best guide, the best way you will ever understand what it's doing is to just have a little bit of an understanding of the code base, just enough to be able to take a log line or a metric, look it up and understand, oh, okay, that has to do with the bit where the coordinator is working out what the result is. Or that has to do with the bit where it's reading data off disk. That's the commit log, or the commit login writes. Often when we deal with people, this is from a British comedy show, this guy's car broke down and the only way he knows to fix it is beat it with a stick. That doesn't help much. There's like no clear understanding of what's going on inside the car, he's just beating it with a stick. Build an understanding of what's going on. So back to this, what are we going to do? We've got two choices here. We're going to go back and take some more observations, or are we going to take some action? So if I don't understand what's going on, then I'm going to take some more observations. It may be that I've looked at something and went, well, I think that this system here, as in maybe the data that the nodes are returning looks good, that are returning to the coordinator, but the coordinator is giving out the wrong results. That's two understandings I've got that shouldn't work, that don't go fit together. two valid understandings, but they're inconsistent. Or maybe I just don't know enough, and now I'm going to go back and go, okay, I need to dive down further into the read path or whatever it is. And sometimes I'm going to take some actions to validate my mental model. So it might be, if I change this config setting, I expect to see this log line appear or not appear, or this metric to change in a certain way. Or it might be that now I've worked out how to fix things, and I'm just going to make that change. So I've worked this out, and now I'm on to acting. So I'm at the point here where because of X, I think Y is happening, so we will do Z. And if you write that out really simply like that, it's a good habit. So here X is the observations, what I noticed was what I believed to be happening. Y is the orientation because of what, and Z is my decision of what I'm going to do about it. Before I start doing anything, I'm going to test if my assumptions are still true. So has the world changed since I went and did all this stuff and worked out what I think is happening? It's a good thing to start with. I'm going to document the state of the cluster before I start. And the really easy way to do that is just take the node tool status output and dump it into a ticket or put it somewhere so you know how many nodes there were, what state they're in, or maybe dump out node tool gossip info or something like that. Really handy if you ever make a change and unexpected things happen, to be able to go back and reverse what happened by having a clear starting point. And then we record the changes that we made somehow, just copy and paste some things, the time that things happen, that type of stuff. And then at the end, test my predictions from the change and go back if needed. So I think by having a little bit of an understanding of the code base, just enough to find log lines and things like that, I might be able to understand that if I change the config setting, I now expect this log line to appear or not appear. I expect the metric to change in a certain way. And I'm maybe just trying to understand what's going on, whatever it is. But there were some predictions that I had that now I'm going to run. And then if you're not done, then you're going to loop and go back again. So it has these little feedbacks here. You could be doing this again and again. We're just trying to put some structure into our problem-solving approach here, trying to build a way for us to work as a team as well. So I'm going to go back and do this again if my predictions aren't working. So have I fixed it? For example, are the nodes now available? Was I just testing to see if my mental model worked? Whatever it is. Return back and restart. We don't follow all that much. I mean, we do it our own way. We do it, we write those headings out, we do all those things, but we don't follow this because we're not in the Top Gun fighter school. So we take the idea and we do it our way. And we do it with all those headings and we do it the way I've described it. We don't follow that picture perfectly. Really, we have our own I have my own OODA loop in here as well. And this is what I think I'm doing, and this is what I think I'm doing, and the result is the stuff I've just explained to you. So I'm going to start with a guess, and then I'm going to continue to bisect the problem as I test my guesses. I'm going to build a mental model of what I think is going on by understanding the config and the metrics and the outputs and a rough understanding of the code. And I'm going to make some predictions so I can test them. And then I'm going to look for evidence of those predictions, maybe by going and looking at other metrics or making changes on the canary node. We often do that, like if there's a larger cluster, go and break one node, not all of them. It's a really good thing to do, especially with upgrades and things like that. And then I'm going to make changes based on the evidence of that. And there's lots of evidence that you can get hold of. There's some reasonably good documentation on the Apache site nowadays that DataStax's gifted. So all of the command line tools are there, and it's even been updated now, which is great for an open source project without having a vendor paying people to do it. So there's lots of ways that you can get evidence and understand what the system's doing. And then you just go back and keep repeating this again and again until you get done.